In this lesson, we're going to focus our attention on understanding appropriate mechanisms that are in place to enable input and output and stable storage through the mechanisms in our hardware and computing systems. And so for this discussion, we've built on the network protocol stack, and now we will dive into appropriate details related to input and output, as well as persistent storage mechanisms. And so you want to consider that when we're working with the computer, we'll have appropriate mechanisms in place, specifically our device controllers and input and output devices, such as your keyboard, monitors, and mouse. And so our device controller is what is able to provide for the interface to our CPU and chip. And then it is also able to provide for appropriate interface to our input and output as well. And so this is kind of considered a generic component, but what we can do is build on it to understand the specific device characteristics that come into play. And so we want to consider, how does the CPU talk to the controller? In this extent, we have memory mapped IO, we have load and store instructions that can be used as an alternative to special IO instructions. And so what are some ways in which data movement is affected? Well, using program IO can result in slow speed, but if we use DMA and interrupts, we're enabled to get higher speed. And so what are some of the devices that we can enable this for? It can be for the camera, for display, for audio, and other specific device components. So let's consider a keyboard device. What you'll want to recall about the device itself is the circuitry mechanisms that come into play and the encoding that's required to represent appropriate characters. And so when representing characters, we utilize the ASCII standard to convey information to the computer. And so we need to consider what is needed in order to accomplish this. And we need specific temporary space to hold the characters that we're utilizing. And we're also going to need to be able to have a mechanism that can be utilized to grab the attention of the processor for characters that need to be processed. And so in this extent, we have our controller and we have our device. This can somewhat result in slow device speed when it's serviced with program IO or PIO. So what we want to make sure is that for representing the information, we need to have an appropriate byte in place to determine if we have information that's waiting in the data register, and that would be our ready bit. We'll need to have an instructional fetch to ensure that the device has signaled an interrupt. And then we want to have an IE if one interrupt it's going to be one if the interrupt is ready. And so if we were to represent this in our system, we will have our ready bit to represent the question of, is this going to be a character in the register that's new? And then we'll also want to have our appropriate interrupt enabled as well. And that will just basically ask, is the processor allowing the device to execute? And so with this in the consideration, if the interrupt this process will have specific commands that will execute. We'll need to set the interrupt enabled. We'll check the ready bit to see if it equals to 1. And then we'll need to load the key code from the data register. We're also able to utilize this with memory mapped IO. And so in this representation, what we'll have is a processor memory model that can be used in order for the processor to read and write to memory using load and store instructions. So in this sense, we'll have our data registers and status registers that are assigned to the device controller. And so if with knowing the addresses for those registers, we can use the same load and store instructions to manipulate them. So this allows for us to use memory mapped IO to provide for interaction between the processor and appropriate device controllers without any change to the processor state. And so in order to accomplish this, we will need specific commands. We'll need to be able to check for new data that might be available. We'll need to be able to read data. And then we'll also need to be able to set the interrupt enabled bit. And so using these commands, we have appropriate mechanisms in place to move data on the address bus. So now we can consider what mechanisms do we have for programmed IO, and that we want to have an interface that is able to connect to the device controller and to the processor. This allows for data to be moved back and forth between a device and the processor. And we have specific programming instructions that enable us to accomplish this data transfer. So in this sense, we can use the keyboard example to show the various commands that we can utilize. So typically, keyboard, mouse, and other components might have slow device speeds. And so we'll have the CPU execute the program for moving the data as necessary. And this is often done using polling. And so if we have our appropriate load instructions and branches and store instructions, usually the load will clear the ready bit as a side effect of reading the data register. But during this process, we're busy waiting, which can also waste processor cycles. And so what we can do is have this be interrupt driven, and upon an interrupt, the handler code is then executed. When considering high-speed devices, we want to understand that once a command is given by the CPU to the controller, then data needs to come in continually. And this can be as a result of streaming. Program I/O has a potential for data loss if the CPU doesn't poll or respond to the interrupt quickly enough. So therefore, streaming devices move data to and from memory autonomously. And so what is the CPU to controller interface? We need to be able to convey commands, read and write, interrupt enable, and then we also need to be able to check the status for any errors that may be present as well. And so you'll want to recall with direct memory access, we're able to utilize our device controller to transfer data between itself and memory. And this enables this to occur without any involvement from our processor. And so with the processor to the controller, we can move specific bytes from our disk location X to memory location M. And so what other registers might we need? We'll need appropriate registers to store command, count, device address, memory address, as well as status. And so all of these represent appropriate unique memory addresses. And so let's consider an appropriate program that we can use for conveying I/O commands. So if we want to transfer in n bytes of data from a memory buffer at address M to the device at address D, then we have the CPU execute appropriate instructions. And so we can have a number of different instructions where we store in into our count register. We can store our memory into our block number into our device address. We can store our write to the device command into the command register. And then we're able to set our status register as well. It should be noted that these are representative of appropriate memory store instructions. So at this point, the CPU's work is done and the device controller takes over to do the actual data movement. So as an aside, modern CPU chips already contain device controllers for our PCIe devices, and this allows for the sharing of on-chip memory controllers with the CPU cores. And so with DMA, what we're considering is we have the device controller is like a CPU. Internally, it has the data path and control to implement each of a set of instructions for our processor. And so we have our memory map registers that can interface with the CPU. And then we have our appropriate buffers that can be utilized for streaming from and to the device. And we have our CPU and device that compete for bus cycles for access as well. And so it's important to keep in mind that with these components, we're able to provide for appropriate data transfer with the controller accessing the memory bus. And typically this can occur with in contiguous bytes, starting with the memory address that is going to need to be utilized. So once we've set our buffer and it's ready, we can initiate the transfer of the buffer contents into our devices. And so when we consider some of the appropriate data transfer speeds, we want to consider how fast they can transfer. And so our data rates around the year 2008 for keyboards were 5 to 10 bytes per second. And presently it's still 5 to 10 bytes per second. And you want to understand whether it's effectively utilized using programmed I/O or if it's going to be utilizing DMA for us. And so for keyboard and mouse, they still rely on program I/O, which has effectively kept the same rate. Other mechanisms, graphics display has stayed the same. Hard drive speeds have increased significantly. Network speeds, of course, have increased significantly. Modem speeds have remained pretty consistent, and other peripheral devices, printers and whatnot, have remained consistent. Flash memory has improved by a factor of 10. And you want to notice that in each of these cases, the improvements have been made thanks to direct memory access. It's also important for us to understand how device drivers interact with the operating systems. So our device driver is going to be a part of our operating system, and we want to keep in mind that we have a device driver that is going to essentially control each device in our computing system. So here we're able to see an overall system breakdown of the relationship between our device drivers and the rest of the operating systems that can be utilized in system software. And you can see that we have our CPU scheduler, IO scheduler, system call and trap interface, as well as appropriate interrupt handlers and trap handlers too. And so with our device drivers, this is going to be a part of the OS that issues our commands for devices. And it can be very much device dependent since each device is going to need their own driver. And so in this case, we can consider an example of a device driver for a camera that enables pan, tilting, and zoom. Specifically, the device driver is going to control the memory map commands that are needed for the CPU to specify appropriate functions for the camera, which could be zoom, tilt, adjusting the X and Y coordinates and whatnot. So these are all commands that the driver has control over and can be implemented using DMA for the data transfer. So now we want to focus our attention on our device for storage, which is going to be representative of our disk storage. And so disk drives have gone through a strong progression with technology in regards to being able to store at a quicker data transfer speeds. And so typically when you think of a modern disk drive, you're going to have specific components that are represented. You'll have platters that are going to be aligned and coated with metal. You'll have appropriate spindles that are utilized. And then you'll have an array of magnetic heads that are used for reading and writing to the disk. And so you'll have your recording head stack, the shaft that's utilized, one of the platters, the drive motor, head position. And so if you want to break these down in a more component type level, you can have your platters that are aligned, and each platter is going to have specific tracks on it where the data is recorded. And then it's also split into appropriate sectors. And so in this case, it's important to keep in mind that you can also record on your disk drive on both sides of it. And so you'll notice that the tracks, the outer tracks, have more space to store more information than the inner tracks. And so they're going to have a larger footprint. And so with using a cylinder, this means that all of the tracks can be accessed without any specific head movement. And so a typical disk drive to seek can be accomplished in 7.5 milliseconds, rotation in 4 milliseconds. The surface size is going to be 1.75 terabytes. The transfer rate, 600 megabytes per second. And so based on those stats, you want to say, how long does it take to find a random block on the disk? It'll be the seek time plus the rotational latency divided by 2. So in this case, it would be 7.5 milliseconds plus 2 milliseconds equals 9.5 milliseconds. Then you want to consider roughly how many random reads can you do per second. And this means it's going to be 1,000 milliseconds divided by 9.5 milliseconds, which will give you 100 reads, or similar to 100 reads. And so, and the data transfer rate, if blocks are 4K bytes, it's going to be 100 times 4,096, or 409 kilobytes per second. And so what you'll notice is that that speed is going to be slightly different from the maximum transfer rate. So we can further get into some specific metrics associated with our disk drives. And if we have, consider that we have P to represent the number of platters, N to represent the number of surfaces per platter, T to represent the number of tracks per surface, and S to represent the number of sectors per track, and B to represent the number of bytes per sector. To this extent, we can compute the capacity to be P times N times T times S times B, bytes, and that'll give us the total capacity that we can store on our hard disk. So let's consider that we have a hard disk that has 512 bytes per sector and 12 sectors per track, 100 tracks per surface, 2 surfaces per platter, and 6 platters. We want to consider what is the total capacity of such a drive in bytes, and how many cylinders does the device take. So we have our appropriate metrics in our problem. We have P, we have N, we have T, we have S, and we have B. And so if you recall, we have our capacity represented as these metrics multiplied. And so it is going to be equal to 7,200 kilobytes, or 2 to the 10 bytes. And it has T cylinders, which are 100. So if we want to consider some additional transfer metrics, we have R for our rotational speed. We have S, which is going to be, again, the number of sectors per track, and B to be the number of bytes per sector. And so the time for one revolution is 60 divided by R. The amount of data read in one revolution is going to be S times B bytes. The data transfer rate of the disk is going to be the amount of data in a track over the time for one revolution. And the data transfer rate is going to be S times B times R divided by 60 bytes per second. So let's consider an example. Given the following specifications for a disk drive, 512 bytes per second, 400 sectors per track, 6,000 tracks per surface, 3 platters, a rotational speed of 15,000 RPM. What is the transfer rate for this device? So you want to recall that our data transfer rate is going to be equal to S times B times R divided by 60 bytes per second. So we have B, S, and R provided for us. And so that is going to give us 400 times 512 times 15,000 divided by 60, which is 51,200,000 bytes per second. And a little bit of history, we have the first magnetic disk drive that was unveiled. This was announced in 1956. It had 50 platters, 3.75 megabytes, 1,200 RPM, 8,800 characters per second, and weighed 2,000 pounds. It was a part of the IBM 305 RAM Mac, and it's at the Computer History Museum in Mountain View, California. So here is a useful link that shows a video of this first magnetic disk drive. So if we recall in history in the early 60s, the disk pack was around 5 megabytes. You had your read, write heads, and access arms, and they were magnetic disks. And so this is from the IBM 2311. And then you also had a removable Memorex disk pack that was available too. And you have to consider this was when computers were largely very, very big. So let's consider, why are disk drives sealed? Since the early 60s, read and write heads are aerodynamically shaped, so they fly on a very thin cushion of air. So any type of obstacles are not well tolerated. So any type of smudge or wind or whatnot could cause appropriate errors. So you want to consider appropriate mechanisms for recording. And so one mechanism is called zoned recording. And in this mechanism, we make use of an appropriate zone bit recorder that is used to keep a footprint of a specific sectors for the entire surface. So the outside track of a platter moves faster than an inside track. So this allows the outside tracks to hold more data, as we previously said. And with zone recording, it assigns more sectors to the outer tracks. With this scheduling, you have to consider the ordering of disk requests is quite important for I/O performance, just as job scheduling is important for CPU performance. And in this case, we need to seek the rotational delay and understand mechanical components that are utilized. This can create a huge advantage in terms of the speeds of memory and the CPU instructions. So that's 5 times 10 to the negative 3 compared to 1 times 10 to the negative 9, or more than 6 orders of magnitude. We also have to keep in mind that as disk controllers have become more capable, that I/O requests are queued for them by the OS. And disk controllers may have 31 pending I/O operations queued and perform their own scheduling on them. So we're going to bypass discussing those metrics for disk scheduling, but just make sure you understand that there are many algorithms similar to CPU scheduling. And so some prominent algorithms are FCFS, which is self-explanatory for you. Because we'll always denote for it being first come, first serve, which is one of the foundational scheduling algorithms. We have shortest seek time first. We have the look algorithm, which keeps going the same direction until no more requests are made in that direction. We have a scan algorithm, which is similar to like an elevator algorithm, like look, but always goes to the top and bottom floors of each trip. We have C-scan, then we also have C-look. So some appropriate implementations for first come, first serve. In that, you know, it has a benefit in that it will, that anytime a request occurs, the one with the least variance in waiting time will be utilized to request the IO. Shortest seek time first is going to be similar to SJF processor scheduling, in that as shortest seek time seeks to minimize the average wait time for a given set of requests. We have scan as well, which is going to be similar to our elevator algorithm, and that is going to start at a specific position that's going to be towards the innermost of the track, and as the head moves, the algorithm services the requests that are en route from outermost to the innermost, and it does this regardless of the arrival. And we have our C-scan, which can utilize the disk surface in a circular manner. So it will rotate until the head reaches the innermost track, and then the algorithm will not service any requests in the reverse direction. Then we also have C-look, which provides for appropriate policies that are similar to scan and C-scan. So we also have appropriate solid state storage devices that we are going to overview very quickly. These have become effective replacement for small and fast storage applications. And so they act like hard drives and are faster but more expensive. And so they have a typical capacity in comparison to our typical hard drives. Can go from 1 to 18 terabyte. SSD can go from 0.25 to 15 terabyte. IOs per second can be 400 for a hard drive, but solid state devices can be 13,000 to 70,000. Max transfer rate, 500 megabytes for our hard drives, but up to 3.5 gigabytes for our solid state devices. And so also they have a quicker seek time as well as lower energy use. So this provides a means for why solid state devices might be better options over our typical hard disk drives. And so also we want to consider our composition for system boards. because the system board is a key component of how all of the components in the system come together through not only program IO, but as well as in terms of the IO processors and whatnot and the CPUs that are utilized. And so here we have a depiction of a modern dual x86 server system board. And the system block diagram shows you the circuitry and bus interconnects between chips, as well as other components that are available. The PCI slot set can be utilized, the DDR RAM that's available as well. And here is another x86 server using AMD chips instead. And so this provides us with an overall high-level view of how all of the components that we've reviewed throughout the course come together in a modern system.